Hi class. In this lecture, I will talk more about the dual related to the weak duality theorem and the duality theorem, and also I will review the dual formulation rules and give one example for you. We start from the weak duality theorem, a minimizing problem for any feasible solution y and x of the primal and the dual respectively. W is larger than or equal than z. Further, W equals to z if and only if these two conditions. So maybe you will confuse that why W is larger than or equal by z. Okay, because now we talk about the minimization problem. For example, if this line represents optimum value for minimizing problem, right? So this region belongs to primal, and this region become to the dual. So W here, W is the value in the primal, and the Z is the value in the dual. So W always larger than dual value, right? If we start from the maximizing problem, so it will reversed. Okay. So now we try to do the proof. So first one, because it's a minimization problem, so in the standard form, we will introduce a non-negative surplus variable ym plus 1, ym plus 2, till ym plus m into primal. Then original here is a larger or equal sign become the equal sign, right? So, and this one is the original constraint and introduce non-negative surplus variable. Okay, and in both sides we times x, right? So for the first one we times x1. For the second one, we times x2, and so on. Okay? Okay. And then now we try to do the W minus Z. Okay. The final result, we want what? We want to W minus Z greater than or equal to 0, right? Then we will get W greater or equal than Z is what we want for weak duality theorem, right? Okay, so W minus Z, here is the objective, here is the objective as well, right? Okay, then we try to put the coefficient for x1, x2 till xn, and here is not related to the x. Okay, so then we combine all of the xj. Okay, so this one, okay, this one here, we have the y1 here, we have the y1 here, we have the y1 here, right? So we can further to make all the y1 here and try to make the coefficient for y1 and for y2 and till ym, and the rest of the items are this one. Okay. So because now for dual formulation, okay, Here we have primal formulation. This one, our dual formulation, is equal z is summation bj xj, and the standard form of the constraint is here. So we can move ci minus summation j a j i xj is what? It's larger than 0, right? So in this item, all of this one are greater or equal than 0, right? Larger, right? And this one is definitely larger than 0 because for x and for y are non-negative. So all of the number are larger than 0, of course. This one are validate. Okay. So this one is the result, right? All of this one are larger than 0, and this one is definitely larger than 0. Okay, so we have the weak duality says that for minimizing problems, W always larger than maximization problem. So what about when the W equals to Z? Okay, if W equals to Z, which means all of the item is 0, including this one, right? So is that possible? The answer is yes, right? When the C1 equals to this number, C2 equals to this number, all of this number, okay, all of this number times y equals to 0. Okay, all of this number times equal to the 0, and ym plus jxj equals to 0, right? But we still need to prove, right? We need to prove this number is equal to 0. But now, what is the value here is summation ym plus jxj, j from 1 to m. But if you back to this slide, you can see we can move this one into right hand side and move this one to the left hand side. So what is this one? Actually is bj, right? Is this item, right? If you put j equals to 1, then you will get the first equation. If you put j equals to 2, you get the second equation. So basically, this one is this one, right? So when the bj minus summation I a j I y I times xj and the ci minus a j I xj y I equals to 0, that will cross the w equals to z. So under this condition, we says that the weak duality theorem become duality theorem. Okay, so now we have another corollary theorem, okay, which will represent unboundedness and infeasibility. Okay, so here there is a lot of sentence I just read. Okay, if the primal linear program is unbounded, then the dual linear program has no feasible solution. Okay, so since any value or objective of minimizing linear serves as an upper bound for all value or objective of the dual maximizing linear program, it is clear if maximizing problem is unbounded, then the dual minimizing have no feasible solution since they will produce an upper bound. This situation analogs for an unbounded minimization. Okay, so we can see we say that W is less than Z, right? So if this one primal is unbounded here, right? This one is unbounded. So W cannot exist, right? Cannot exist because it should be the upper bound. But actually, Z is unbounded. So that represents this, what I said, this sentence. Okay. So we can just use this very short sentence to represent the proof. And the others are for optimality. Okay, so if the objective function value of Z and W corresponding feasible X and Y in dual and primal respectively are equal, okay, now are equal, then the X and Y are optimal solution for the respect problem. Okay, so what is the proof? So since an objective function value of either problem is a bound for all solutions of other problems, if two values are equal, the objective value are neither can achieve any better value because they are primal and dual with each other. So if these two are the same, actually it cannot become better than the other value. So what is the condition in optimal condition? Okay, so finish the proof. And just when we prove the duality theorem, we use the two relationship. One is Bj minus summation Aj y I xj equal to 0, and the Ci minus Aij xj y I equals to 0. We call it complementary slackness. Okay, so basic, it can determine the feasible solution of dual and primal in optimal solution, and this condition is if and only if. I already do the proof just. Okay, so this one we will call it complementary slackness. Okay, so repeat again the theorem, the duality theorem. The objective function of minimizing problem takes on a minimum value if and only if the objective function of dual maximizing problem takes a maximum value and they exist. Two optimum value are equal. Okay, so just repeat again. So now, remember in the last lecture we have the seven principle. Okay, and now I list these principles into the rules for you. Then you can use these rules to transfer the primal into the dual. Okay, so we start from the minimizing. Okay, in 8y1 plus 10y2 plus 4y3 subject to 4y1 plus 2y2 minus 3y3 greater than or equal to 20, 2y1 plus 3y2 plus 5y3 is less or equal to 150. 6 y1 plus 2y2 plus 4y3 equals to 40, and y1 unrestricted, y2 and y3 are greater than 0. Okay, we just step by step. First one, we try to transfer the minimization problem to maximization problem. Okay, so the right hand side of the constraint will become the coefficient in the objective function. Okay, so here is 20, here is 20, 150, 150, 40, and 40. Okay, and second step, we have the first constraint for the dual is the first item's coefficient. So here is 4, 2, 6. Here's 4, 2, 6. And objective function become the right hand side of the dual formulation. Okay. And because y1 is unrestricted, so we see the ith variable are restricted. So the ith constraint, okay, is equal. So we use this one as a principle. So here is equal sign, okay. And for the second one, is the same. Basically, it's the same, but we need to check the variable here is larger sign. So it's larger sign, then the constraint will be less sign here. So here it will become less than or equal, right? So for the third, it's still the same. Okay, very similar to the second constraint. And then we need to determine the variable. Okay. So for the sign larger than, so here is the constraint larger than the variable is greater than 0. Okay. And the second one is less than. Okay. So less than is here. So the variable is less than 0. Okay, and the equal sign here is unrestricted. Okay, so x3 is restricted. So according to this table, we can transfer the primal to the dual. Okay, and the vice versa from the maximization problem to the minimization problem is also you can use this table. So after this class, please use this table and just find a problem and transfer from the primal to the dual by yourself. Of course, in this class, we use the games program. We don't need to worry about the primal or dual. Just put the primal formulation into the games and we can solve. But for the class, if you want to have a solid knowledge about mathematical programming, about the linear programming or mixed integer programming, definitely you need to know a lot of the theorem, a lot of proof, and a lot of principle. Okay, that will help you to change your mind and know the basis of this course. Okay, hope you enjoy this table and to know the weak duality theorem and duality theorem. Okay, see you in next lecture. Bye bye.